I'd like to talk to you today about the results of the RATE project. RATE stands for Radioisotopes in the Age of the Earth, and I've entitled this talk, and this is the first time I've given this talk, by the way, Thousands, Not Billions. And that's kind of a takeoff on a Carl Sagan statement, billions and billions of years ago. But it's thousands, not billions. But at this point, we are finishing 8 years of research for this research project, studying the radioisotopes and the age of the Earth. This was one of the most, and has continued to be, one of the most difficult problems for creationists to deal with, because it seems to most of us that there is a lot of authority based in estimates of the age of the Earth, particularly rocks, based on radioisotope dating. And many people have thought about this problem. Individual creationists have worked on it, but no one has really made breakthroughs in this field until this project came along. And we grouped a number of really leading scientists in creationism together over the last 8 years to try to work on this problem. And the Lord has provided fantastic answers to this, and I want to be able to share this with you today. This is the RATE group. I'll go through real quickly. From the front row on the left is Dr. John Baumgartner, PhD in geophysics, recently retired from Los Alamos National Labs, now working full-time at ICR. There's yours truly next to him on his left, your right. And then the bearded one is Russ Humphreys, PhD in physics, recently from Sandia National Laboratories, and he is now retired from there and working for ICR full-time. On the far right is Dr. Gene Chaffin, a physicist, teaches at Bob Jones University. Behind him in the second row is Dr. Don DeYoung, a physicist at Grace College and Seminary in Winona Lake, Indiana. Right in the middle in the second row is Dr. Steve Austin, PhD in geology at ICR. His right is Dr. Andrew Snelling, PhD in geology. His specialty is in igneous geology, that is the kind of rocks that come from magma. Dr. Austin's specialty is in sedimentary geology. In the back left corner is Dr. John Morris, the president of ICR. To his left is Dr. Ken Cumming, the dean of our graduate school and in charge of the overview of research associated with the graduate school. The tallest one in the back is Bill Hosch. He's our technician, master degree technician in geology, who does a lot of the legwork out in the field and also a lot of the sample preparation in our laboratory. And in the far right corner is Dr. Boyd, forgot his first name, Dr. Steve Boyd, a theologian from the Master's College, and added a really special part of our project in doing a full statistical study on the poetic and narrative portions of Scripture, showing that Genesis, the parts of Genesis that talk about creation and the flood, are narrative and should be taken literally and historically, not in an allegorical sense. We'll talk about that a little bit. This is the book that will be coming out this fall. You saw one on the table back there probably. That's our Rate 1 book, you might say. It came out at the end of the first 3 years of the project, in which we had spent 3 years preparing what we were going to do, and we laid out the proposals for the research that we were going to have, and we published that book saying this is what we're going to do, and we spent then 5 years, which ends this year, and this book then is reporting on the results of the full 5 years of research that we did in the last 5 years. It's a slightly different color scheme so you can recognize it from the first. It's got a volume 2 at the top to help identify it as well. And you'll notice down here in the title, the subtitle, it's Results of a Young Earth Creationist Research Initiative. The first one just said a Young Earth Creationist Research Initiative. Okay, this project started out and really was dealing with a significant problem. And it had to do with whether the earth is thousands of years old, as the Bible would teach or teaches, or is it billions of years old, as the conventional scientific community would teach and believe. And the age issue really says that evolution requires long periods of time to operate, if it's even going to operate. And what concerns us most is that some Christians have accepted the evolutionary idea, and it's a major compromise and trying to put the long ages together, which would allow for evolution if it could occur, which I don't think even with an infinite amount of time evolution could occur, but at least it gives it some credibility. The total effect is exactly what Mike Riddle said during his last hour here, and that the effect is to degrade the reliability of Scripture. Because if you can't believe in the world that we can see, how can you believe in things that are spiritual that you cannot see? Does that sound like a familiar statement? That came from Christ himself. Well, the question then, is the earth really old, or is it young? There's some basic assumptions of radioisotope dating. And by the way, radioisotope dating really only started about 100 years ago, when radioactivity was discovered in about 1990 or 1895, and then developed over the next 100 years or so. But there are three basic assumptions when you go to use radioisotope decay as a dating method. The first one is that there was no initial concentration of a daughter element. Now I have to define some terms here. There are something called parent elements and daughter elements. A parent element is the radioisotope that is unstable and is going to decay into some other materials called daughter elements. For example, uranium decaying into lead. The uranium would be the parent, the lead would be the daughter. It's also assumed that this decay occurs at a constant decay rate, that it's always been the same as we observe today. And finally, that this process is in a closed system, that the amount of parent element has not been added to or subtracted by other processes than radioactive decay, and the same thing is true of the daughter elements, that there's no such thing as diffusion or removal of material, contamination, all that sort of thing. It's a very closed system. Well, it turns out you can't prove any of these things, and you have to assume them. You can get some evidence to try to make that less likely, but you never know for sure because it happened in the past, and we have no way of knowing for sure. As opposed to those basic assumptions, the rate group developed some hypotheses, and these are just a few of the hypotheses that we started with. The first one, which was truly a hypothesis when we started, and it was because the group itself, when we first got together, had some preconceived ideas as to what we might be facing, and suggested that in order to be able to reconcile the thousands of years of the Bible with the billions of years that current conventional dating techniques develop, you would have to have some kind of a change in the decay process, or the rate at which the decay occurred. And this became known as accelerated decay. So we assumed that we needed to do experiments to be able to try to determine whether this was true or not. It was truly a hypothesis. It wasn't even a theory. It was made almost a conjecture. Is it possible that decay has changed in the past and been speeded up in some way? Now, you may not realize how controversial that is. The rate of radioactive decay in the general scientific community is assumed to be constant, period, and there's no way it could change, because observations generally show, until quite recently, that the decay rates are much less, have changed much less than 1%, even under extreme conditions, like high temperature and high pressures and various chemicals, all kinds of things. So to even suggest that decay rates have been changed or accelerated was very, very controversial. We also hypothesized that maybe some of the daughter elements were primordial. That means that there was some daughter element, like lead there to start with, that maybe you didn't have to start at zero with the daughter. Maybe God created the elements with a certain amount of uranium and a lot of lead to start with. And therefore, this might solve the whole problem. You might be able to kind of offset the clock or give it a starting point so that we wouldn't have to worry about all these billions of years. And then thirdly, we assumed, or we hypothesized, that radioactive processes have produced evidence of accelerated decay. Now, at the point that we did this, we had no idea whether we would actually find this evidence. We were going to go looking for it to see if, in fact, that was the case. Now, I can't tell you how much we had to step out in faith to be able to do this, because we recognized how controversial this was. We even adopted a portion of Scripture, which I'll quote a portion at the end of this talk today, having to do with David standing before Goliath. And David had the gall as a young teenager to stand up to Goliath in front of the whole country of Israel and the nations there, and to defy him and take him on, a giant that was twice as tall as he was. And he ended up prevailing. Well, we didn't have any confidence that we were going to prevail, but we had trust that the Lord would provide, and we prayed in a very special way that he would do so. And we were just gratified when the Lord did provide, and providing answers for us through this project. We prepared a number of samples that we sent out to laboratories, and I must say at this point that this project raised $1.25 million for this work over the 8 years. That was another thing that we had no confidence in. In the past, probably the largest amount of money that we'd ever raised to do research was something on the order of $10,000 or $20,000. Even to think about raising $1 million, which is what we expected this project would cost, was presumptuous, we thought. But yet we depended upon the Lord to provide it, and he did. He provided the money exactly when we needed it, in the amount that we needed as we went along. And we came through the whole project with everything completely covered. Just amazing. One of the things that we did, though, in preparing our samples, rather than having a laboratory, which would have cost more money than even the $1.25 million to do, and having technicians that were constantly prepared to do all kinds of analyses, we didn't feel that that was a good use of the Lord's money, to have a lab that would do a few samples and then never be used again. So we decided we were going to send our samples off to commercial laboratories, university laboratories, and government laboratories, and pay a fee to have the work done. There was also another reason for doing that, and that was that if we had done it in our own lab, one of the criticisms that would have come would have been that we doctored the results. So we wanted it done in a laboratory that had a good, solid foundation, had a reputation, and could defend the measurements. So what we did was we collected the samples in the field, we prepared them in our laboratory where we ground them up like this, and we then sent them to the laboratories, got the results back, and then interpreted them and then write the report. There was all kinds of work, special work that had to be done, even in preparing the samples. We had to break the rocks up, which doesn't take a lot of smarts, just a big sledgehammer. Have you ever seen a mortar and pestle made out of iron? That's how you break up rocks. It's like what doctors use to crunch up pills and stuff. But here you have to have larger equipment and really heavy stuff. And it takes a strong back and a weak mind to do that. We all participated to a certain degree. I'm not even suggesting that Bill Hoche has a weak mind. Don't go there. But he was very helpful in doing the sample preparation. But it took a lot more than that. In order to separate the various grains and minerals in these rocks, we had to use special techniques of flotation. First of all, you run them through sieves at different density of mesh, and separate them out that way. And then you also have to put them into what are called heavy liquids, so that the liquid is intermediate between, say, two kinds of minerals, so that certain minerals are more dense than the liquid and fall to the bottom. Other minerals are less dense and therefore float to the top, and then you separate them. You can also separate them if they happen to be magnetic by using magnets. One of the most frustrating things that we had to do was to do it under a microscope with a pair of tweezers and separating out individual little grains of crystals. So there's a lot of work involved in this process. These are some of the stuff from the labs. Okay, now what I'm going to do is give you an overview of the results of the RATE project. And the first one I'm going to talk about is Dr. Russell Humphreys, his work on the diffusion of helium. Now, helium is also a daughter product, for example, from the decay of uranium into lead. When uranium decays into lead, it not only produces lead, but it also produces helium at the same time. The alpha particles that are produced are actually the nucleus of a helium atom. So when it then collects a couple of electrons, it is truly a helium atom. This helium then is embedded in the rock with the lead, but it's a gas and diffuses out through the crystal structure, the crystal lattice, out in the rock. We had already known from some work that Dr. Robert Gentry had done that many of these rocks that we were going to be studying still had a lot of helium in them. Now, you know that if you've ever bought a balloon for your child, or maybe you're young enough you've had your parents buy you a balloon, you know that if you tie it to the bedpost and you wake up the next morning, the balloon is kind of deflated and falling down toward the floor. It's because the helium is such a small atom that it can diffuse through the actual molecules of the rubber in the balloon. It does the same thing in rocks, not as fast as going through the balloon, but at a very fast rate compared to other type gases. And if, in fact, the rocks that we were studying, which many of them were conventionally dated to be 1.5 billion years old, based upon the amount of uranium and lead that was there and the measured or known rate of radioactive decay of uranium into lead, there should be no helium left. It should have all diffused out. And yet there was a lot of this helium still left in the rocks. Now, many of the rocks that we dealt with had embedded in them zircons. These are little crystals of zirconium silicate. And they are very small. They're on the order of 100 microns in length or less. 100 microns is about the diameter of the hair on your head. So they're very, very small. You can only see them under a microscope. But in these zircons is where the uranium is located, typically in a radioactive sample, a radioactive rock, and particularly in granites. We were looking primarily in granites, in which there was zircons embedded and other material called biotite. But these zircons contained the uranium, and the decay was going on inside these zircons, producing the lead, producing the helium, which then diffused out of the zircons into the rest of the rock and out into the atmosphere. These zircons are very interesting because they have a very high melting point, such that they actually will be drawn into the magma that's in a volcano, shot out the top of a volcano, and then re-solidified. The magma will re-solidify as solid rock, and those zircons have never been melted. They can actually be processed through volcanoes without changing them greatly. Here's what a number of zircons would look like. There you can see the 100 microns. There's some of them are almost 100 microns long. Here's a photomicrograph of one in great space. This actually the smaller dimension, or the width of that, is about 20 microns. So it's on the order of about 50 or 60 microns long, this particular one. And it has these little faces on it, which makes it very interesting to work with. As I said, as the uranium decays, it produces not only lead. It starts off as, say, uranium-238 and ends up as lead-206 or lead-207. And in the process, it goes through a whole decay chain. And in various places in the decay chain, there's alpha decay that occurs, and it produces, for each one of those alpha decays, it produces a helium atom. So each uranium atom, by the time it ends up with a lead atom, there's been 8 helium atoms produced on the way. Okay, now this is a uranium atom with a bunch of electrons around it, and it's going to be exploding and sending out alpha particles, shooting out into space here. Here's an alpha particle made up of 2 neutrons and 2 protons. Let me do that one again. As the alpha particles come out, they shoot out in all different directions, and the little alpha particles, as they slow down in the crystal, they collect electrons and then become helium atoms. Now, these are all embedded inside the rock, and the helium, as it is trying to diffuse out of the zircon, then can diffuse out of the rocks. And it looks kind of like this. Here's all this helium coming out of the rocks at the microscopic scale. Oh, nothing is showing here. Did the other one show? No. You didn't say anything any sooner. Oh, my. Uh-oh. Oh, sorry about that. I don't know whether I'm going to be able to get this to work or not. Well, it worked with my projectors before. Mike, you guys, Mike, you got any suggestions? Mike Riddle? Uh-oh, I'm in trouble. Well, let me try it. Do an F5, you mean? Let's see if that'll work. No, that's too bad. No, that didn't do it. Nuts. Well, nuts. Oh, that's going to be one of my special features. Yeah, that's right. Well, okay. We'll keep going here. Sorry about that. For those of you that just got to see the animations, I'll have to show you privately, I guess. I can see it on here. Here, you want to see? Oh, okay, well, at any rate, when we went to get samples of granite, we were able to get samples from a coring that was done near Los Alamos National Labs that they had done in a geothermal hole. And we had samples in granite all the way down to 4,000 meters. That's about 12,000 feet down in the ground. This is actually data that, again, Robert Gentry had originally obtained. And as a function of depth, the sample was at different depths. Here you can see samples 1 through 5 and the depths of them in meters down to almost 4,000 meters, which is 12,000 feet. And the temperature increases as you go down, and therefore the helium that's produced in this granite by the radioactive decay will tend to diffuse a lot faster at hotter temperatures. Up near the surface, we found that, and it's actually 1,000 meters below the surface, that's 3,000 feet down the ground, so it's not right at the surface. The temperature there is already over the boiling point of water in this rock formation, and up to 58% of the helium that would have been produced in 1.5 billion years of radioactive decay was still in the rocks. And yet, very simple calculations based on measurements, very tentative measurements in similar type rocks, would lead us to believe there should have been no helium at all. It would have diffused out much more rapidly, and there should not have been any helium left at all. Even down deep in the sample where the temperature was almost 300 degrees centigrade, there was still up to 1/10% of the amount of helium. Now that doesn't sound like a lot, but it is actually, given the diffusion rates. Well, we plotted this information, a variable called diffusivity. It's a measure of how fast the helium diffuses out through the minerals and the rocks, and this is a logarithmic scale. And I'm not going to go into all the units there, but it's plotted as a function of temperature, and it's in the reverse direction. So it's cooler over here, 100 degrees centigrade, and warmer to the left. This is called an Arrhenius plot. The reason it's plotted this way, it's traditionally plotted this way in the literature, so it's a little hard to interpret. But it allows you to have straight lines on this kind of a diagram if it's plotted properly. Well, you notice up at the top here, well, let me start with the red diamonds. The red diamonds in both here and here are estimated diffusivities based upon the amount of helium that was found in those samples, not from a direct measurement of diffusivity, but based upon how much helium was there given a period of time. For example, for the uniformitarian model, the rock is estimated to be 1.5 billion years old. And if that was true with the amount of helium that was there, you would get this kind of a curve on this diagram. If the rock was only 6,000 years old, which is a creationist number, then it would have been plotted up here, and this would have been something like 4 orders of magnitude or more, almost 5 orders of magnitude difference in the amount of diffusivity. An order of magnitude is a factor of 10. So 4 orders of magnitude would be 100,000 times difference in the amount of diffusivity, and it would have been a much faster rate for the creation model than the uniformitarian model. Well, then the question was, what is the actual diffusivity? How fast does the helium actually diffuse out of rock? Well, we sent it to a commercial laboratory, a university that you would be very familiar with, and had these samples of rock measured for how fast helium diffuses out of the rock as a function of temperature. That's the blue data that we see up here. And notice how well the data flows and matches right up with the creation data that we had from the Gentry information. So we had actually predicted this curve based on the data we got from Gentry, saying this is where we expected it to be, and that's exactly where it fell with a 6,000-year model. Now, we're not talking about a factor of 2 or 3. We're talking about a factor of 100,000 difference between these two, so there's got to be something seriously wrong with the way in which this was done. So now we have an alternative method for estimating how old the rocks are. The standard method is how fast uranium will decay into lead based upon the observed decay rates that we have today. Now we have a new method based upon the rate at which helium diffuses out of the rocks once it's formed. Okay, all right, thank you. Whew. Okay, now what we have here is 2 hourglasses. The one on the left is representing the uranium converting into lead. The upper hourglass and the lower is lead. The right hourglass is helium. We're going to fill the upper part of the hourglass with helium on the right, and it's going to be running down into the lower part, and that represents diffusion, actually. We're suggesting that at some time in the history, you notice the little lever on the left there? It was turned on so that the uranium decay was accelerated, so that there was a tremendously high rate of uranium being converted into lead at various times, probably during the flood, maybe during the first 3 days of creation. At that time, it's producing a tremendous amount of helium, you see up here in the top, going across and filling this upper part of this hourglass, but it's coming down into the lower hourglass as diffusion, not affected by that accelerated decay. Over here now, at some point, the accelerated decay was reduced back to its normal rate that we observe today. Very little helium at all being produced, but there's a residual amount of helium that was put into the rocks, into the zircons and the granite, and this diffusion rate continued at the rate that we observe today, continued at all time. It was not changed by this change in accelerated decay over here. Now down at the bottom here, you'll notice that there are times so that during this process, today it shows 1.5 billion years, where over here on the helium, because it did not change, it shows on the order of 6,000 years, because it stayed at the same rate. Now, we should have more confidence in the diffusion rates because it was not changed by that process. Whatever process caused the decay processes to change rates, it did not affect the rate of diffusion through the zircons. Okay, now then, let's see what happens. Oh, good. That's a little unnerving, you know. Okay, that was the basic, and I'll come back and summarize that a little bit more. Another project that we worked on was with Dr. Snelling, and he dealt with some radio halos that have all kinds of evidence for accelerated decay. We collected rock samples, granite samples from all over the world. This is Stone Mountain in Georgia and Grand Canyon. I went with Dr. Snelling on this particular trip, and I have to warn you, never be a geologist assistant. Because we started at Glacier Point in Yellowstone and walked down through the canyon about 6 miles, and by the time we got to the bottom, I had 50 pounds of rocks in my backpack, and he was carrying the GPS. At any rate, we collected rocks from Yosemite, from Stone Mountain, from places in New Hampshire, in Norway and Sweden, in Australia, various places around the world. We had something like 1,000 samples in which we were looking at radio halos. Now, a radio halo is a little defect in the rock that's produced by the decay of the uranium or other radioactive materials. As it sends out these alpha particles, in addition to producing the helium in there, it also damages the crystal structure and leaves defects or a discolored region in the rock, and it produces this radio halo effect. Now, here's let's see here, how do I do this? Okay, this is a zircon showing kind of how this happens. These are all alpha particles emanating from the zircon, and it actually goes out into surrounding biotite that surrounds the zircon, produces this kind of an effect, and in biotite, which is a kind of a mica, it has layers of the mica so that you can actually peel it off one layer at a time, so that you can get to the point where you're right at a level where the zircon itself is and you can see rings. That's why they're called halos. It's actually a spherical shell of damage, but when you peel it off in the right direction, you get these little surrounding circles called radio halos. The radio halos are actually in these black specks. If you've seen granite, the little black specks is the biotite. In that biotite is where the zircons are located, and the damage occurs in there. And in a process of producing the decay from uranium to lead, there's intermediate chains of material like radon and polonium. Here's polonium halos, and because of water moving through the granite during this process, the polonium halos, the polonium particles are moved downflow from the uranium, and you get these little polonium radio halos displaced from where the uranium is. Now, the importance of this whole issue is that it takes millions of these decays from the polonium center to produce the halo. You don't get you can't see the halos unless there's been millions of these alpha particles produced. And it has to happen in a very short period of time because the polonium only lasts on the order of months at most. It's a very rapid decaying material. Some of them only last a few seconds and minutes, some of the different isotopes, but the longest lasting isotope lasts on the order of months. So these radiohalos, these polonium radiohalos that are produced, there has to be millions of alpha particles. They have to be produced in a matter of a few months, and it has to be in solid rock. If this decays in magma, it doesn't produce the damage. And in fact, if it's produced in rock that's hotter than about 150 degrees centigrade, the halos go away. The damage heals itself. It's called annealing. So you have to have solid rock. It has to be colder than 150 degrees centigrade, and it has to happen in just a matter of a few months. So that means these big plutons of granite that we find like in the Sierra Nevada, up in Yosemite and various places, that rock had to have cooled from a magma to solid rock cooler than 150 degrees centigrade in a matter of weeks or months at most in order for these halos to form. And if you look at the decay rate at which polonium decays today, you couldn't get millions of these alpha particles produced to produce the halo in a matter of months. It has to be millions or billions of years. So again, it would appear that you got billions of years, but it had to have happened fast. So it had to be a catastrophic increase in the decay rate. Again, evidence for accelerated decay. Okay, now we've plotted some very interesting features here. This is radio halo number per slide, and we've actually processed over 10,000 slides in this sample. And they're plotted in numbers per slide as a function of conventional age, based upon the rocks that they were collected from and the conventional age that's assigned to them. And you'll notice that most of the polonium radiohalos occurred in this region here between about 65 million and 500 million years old. We believe those are the flood rocks. Now, it makes sense if you had a catastrophic flood process where all this water was flowing through the rocks, displacing the polonium halos, that it would occur at the same time. So we have very strong evidence that this accelerated decay was associated with the flood. It was not caused by the flood, but it was associated or at the same time as the flood. And it didn't happen in older rocks, according to conventional ages, or in younger rocks. It doesn't go on today. Again, you can't observe that actually going on today. It doesn't happen today. And it didn't happen early in Earth history. It only happened, we believe, at very specific times. Okay, another one, I'm going to have to go fairly quickly here to get through all this. Dr. Austin, for a number of years, even before the RATE project started, was looking at the disparity between ages calculated on rock samples from different locations and for different type tests in the same location. One of the favorite places that he's collected rocks, and we've done many more, is in Grand Canyon. I'm sorry, let me back up here. In Grand Canyon, you have all the various layers that you're probably familiar with, but down in the bottom of Grand Canyon, there are layers that are interspersed with magma that's come through cracks, and it produces these layers of magma, hot magma, that is igneous type rock that is suitable for age dating. Sedimentary rock is very difficult to age date because it's made up of other rocks that were broken up and settled in water and form new kind of rock. But if you have igneous rock, you can date it directly, and you notice it will intersect down in the Grand Canyon at various places. And if you look at the top view, along the Colorado River, there's outcrops of Cardenas basalt and various sills and dikes that are made up of this igneous material. And one of the best ones that we worked at is the Bass Rapids. This is one that Dr. Austin and the RATE group looked at very carefully. Now, this doesn't happen to be at that location, and the samples we collected here were tough instead of igneous rock, but it gives you some idea if you've never been down in Grand Canyon. We take tours there about every 2 or 3 years, and we'd love to have you. The next one's going next spring. Here's a favorite place where samples are collected of tuff, and even the various other government agencies collect in the same place. Okay, now here's a rather complex diagram, and I don't have a lot of time to spend on it, but it's a composite of both Dr. Austin's and Dr. Snelling's data for various types of decay processes. We have in the vertical axis here what's called an isochron age. Now, this is a particular method for estimating how old a rock is using isochron techniques, which is a bit involved. You'll have to buy the technical book when it comes out this fall to get the description of that. And on the horizontal axis is the atomic mass of the material. For example, potassium-40 has an atomic mass or atomic weight of 40. Rubidium has an atomic weight of 87. Samarium and uranium-238, which is way out here. We can then, from each of those techniques, estimate what the age of a particular rock is. Now, these are samples all from the Bass Rapid Sill. The Bass Rapid Sill down the bottom of the canyon. It's the same formation, and the yellow one in particular. You'll notice that there are different dates for the isotope that you use. And you'll notice that it tends to go up based upon the atomic weight. And for some of the other type of rocks, which are granite-like, the green ones, for example, they go up as you go up in atomic weight. There seems to be some interesting trends here based upon atomic weight, which we don't fully understand yet. But the distinction is these error bars aren't even crossing each other. In other words, even for the same type of sampling, we get different estimates of age outside the error bars for the different types of material. Now, the ages are on the order of 1 billion years or so, which we wouldn't agree with, but the fact is that they don't even agree with each other. They're all out of agreement, or what's called discordant. So for the same rock sample, you get different ages based upon the different type of isotopes testing that you're doing. That's quick. I know it's quick, but there's a lot of more information in the books that we're producing. Okay, here's an exciting one. The carbon-14, Dr. John Baumgartner, trying to find carbon-14 in bones and coal. It turns out just about 15 or 20 years ago, a new technique called atomic mass spectroscopy was able to measure the concentration of carbon-14 at extremely small levels, much lower than anybody's ever been able to before. And for about 15 years, there was some 70 reports in radiocarbon, the standard literature for this field, reporting on this, but we didn't find out about it until about 3 or 4 years ago that this was being done. And the reason there were so many reports was they kept finding carbon-14, and there was no way that they were going to admit that the carbon-14 was real. It must be due to contamination in either collection or in the way in which the samples were handled in the laboratory. So they kept reporting this, trying to get rid of all this problem. They never could. They finally come to the conclusion that the technique is valid, that they're actually finding carbon-14. But nobody has had the guts in the conventional community to say, we got a problem. In coal, there should be no carbon-14 if it has a half-life of 5,700 years, and the coal is supposedly 100 million years old. There should be no carbon-14 left, but it's there. It's measurable quantities. Well, Dr. Baumgartner confirmed this by looking, well, let's talk about carbon-14 briefly here. This is in the atmosphere. Carbon-14 is actually produced by cosmic radiation. You got both carbon-12 and carbon-14 in the atmosphere, but carbon-14 is produced as cosmic radiation strikes nitrogen-14 and breaks it apart. This carbon-14 is incorporated into living organisms like plants and animals, just like the carbon-12 is, and the ratio between the two is the same basically as it is in the atmosphere, as it's incorporated by plants, and then animals eat the plants and so on. And then when the animal dies, this carbon-14 continues to decay, so you can actually estimate how long it's been when the animal died as this carbon-14 turns back to nitrogen-14. So you can use that as a dating technique. Okay, now what happened during the flood? If this material in the atmosphere was built into the trees, and suddenly the trees were buried in the flood, here's the flood coming along, burying all these trees, compressing it under the sediment layers and forming coal, then the coal is continuing to decay, and the carbon-14 is turning back into nitrogen-14. And you can date the coal. if there's carbon-14 there, it tells you that the coal is young. And that's in fact what we find. Here's the estimates from, or here's the measurements that were reported in the literature for some 70 different samples. The average value in units of what's called percent modern carbon, it's the number of samples on the upper axis over here, it's just a histogram. The average value of this turns out to be about 0.292% of the modern carbon that we have today, which is something less than about 30,000 years old. The carbon that's actually in the coal tells you that the coal has to be something less than 30,000 years old, and yet the conventional community says it's over 100 million years old. We did some of our own samples. We collected 10 samples from the coal lab at Pennsylvania State University and sent them in for our own analysis, and we repeated that. We came up with an average of about 0.247. So we confirmed that the numbers that have been reported in the literature are legitimate from our perspective as well. Well, while we were at that, we decided, you know, if carbon-14 is in coal, and that's possibly could be contaminated. You can imagine water percolating down through the soil could bring carbon-14 potentially into coal, so you could be criticized as it's not legitimate. What about diamonds? Is there possibly carbon-14 in diamonds? So the first time this was ever done, John Baumgartner took some diamonds, sent them to the lab. Took us about 2 years to get this done because the diamonds in the ovens that they were trying to vaporize diamonds, if you can imagine vaporizing diamonds at several thousand degrees, they kept exploding and destroying their ovens. They finally got a new oven that didn't get blown up, vaporized these diamonds, and they were able to find carbon-14 in diamonds. Now, not quite as high as they are in coal. It was on the order of about 0.1% modern carbon. But we have a very good case here where diamonds are not going to be contaminated. They were probably formed on the order in conventional time frames of about 3 billion years ago down deep in the earth, and the carbon-14 is in the diamond, and it's not going to be contaminated because diamond is the hardest substance known, and you don't have to worry about being criticized for contamination of the diamond, and yet the carbon-14 is there. The estimates are that the diamonds are less than about 50,000 years. Now, 50,000 compared to 3 billion, that's a big difference. Now, you have to understand that there's other processes like the flood that was involved in this that are not counted in conventional age dating. But this information from diamonds has really gotten the attention of the conventional community. By the way, we've been reporting these results at the American Geophysical Union meetings up in San Francisco, and we've been getting reactions from the conventional scientists, and they're just basically scratching their head and saying, boy, you guys have got something here. Keep working on this. This is fascinating. We don't know what it means, but keep going. So we got some encouragement. Okay, just quickly, we've also wondered if decay could be accelerated, how theoretically would that be possible? Well, Dr. Chaffin has looked at the conceptual idea of changing the well depth in the nucleus of atoms and the well width, and he has found that you can actually increase the decay rates by many, many orders of magnitude by just simply making those slight changes. Now, we don't know whether the changes were made that way by God or what actually caused the decay rate to occur, but theoretically it is possible. Now, more exciting than that is, under very unique circumstances, it's now being reported in the conventional literature, under certain situations, decay rates have been able to be changed by many orders of magnitude as well. That's for alpha decay. Dr. Chaffin, yes? I'm sorry, well depth is the potential well inside of a diamond, inside of a nucleus, where the distance between particles can be measured in potential energy, and it's kind of a well. It's called a well in energy. That's a very technical term, so I can't go any more into it right now. Sorry, got limited time here. We've also looked at beta decay, and even though string theory is very theoretical and may not be the final answer, there seems to be some value in looking at string theory to understand that beta decay could be changed dramatically as well. Finally, I want to report on one study here, and then I'm going to have to quit, and that's Dr. Steve Boyd's work in looking at different verb forms in the Old Testament to try to distinguish between narrative and poetic passages. Mike talked about this earlier today in terms of the order of words can help distinguish. Well, he looked at some different forms here. He did a statistical comparison of the narrative and the poetic passages by looking at the frequency of different verb forms, preterite, imperfect, and perfect verb forms. And he found passages in one place that were known to be a literal description or a narrative of what occurred, and then a poetical description of it, kind of flowery and so on, compared those and was able to get a general rule, and then went back and applied this in a rigid statistical sense to all the passages, and then found out what the Genesis passages would be on the creation and the flood. And here's a histogram, sort of, to show you. It's a three-dimensional histogram. For example, Exodus 14 is a literal passage, and Exodus 15 is a poetic passage of the same event. And you'll notice the green here is the preterite verb forms. There's a large number of preterites and a relatively low number of imperfect and perfect verb forms in that passage, and just the opposite in the poetic passage. It had a low number of preterite verb forms and a high number of imperfect and perfect verb forms. He also dealt with wa-perfect, which is a fourth verb form in the back here. He did the same thing in a passage of Judges 4 and Judges 5, and Genesis 1:1 and Psalm 104. Genesis 1:1 is the narrative passage. Psalm 104 is the poetic passage. And same thing on the flood and in Psalms 105. The statistical result of this was that he was able to separate the poetic passages very easily with these verb forms from the narrative passages up here, and there's hardly any overlap between the two. Here's one that's kind of in the poetry form, even though it is considered a narrative. So based on these rules, he was able to get a distinction between narrative and poetic to about the 5th decimal place, so that when you have certain characteristics, you absolutely know it's narrative and not poetic. So we have great confidence that Genesis 1, well, I should have shown that, I'm sorry. Here's Genesis 1:1 up here, very strongly into the narrative portion. So we have confidence that Genesis is a real, literal description of events, not just allegorical poetry. Okay, well, here's the passage in 1 Samuel 17 that I wanted to quote, that we started this project, and we give great credit to the Lord in this. This is David standing before Goliath and taunting Goliath, in a sense, telling him who he depends upon. I come to thee in the name of the Lord of hosts. This day will the Lord deliver thee into mine hand, that all the earth may know that there is a God in Israel. The Lord saveth not with sword and spear. The battle is the Lord's. He will give you into our hands. That's the verse that we took as our verse for this project, and the Lord provided in magnificent ways. It truly is a young world from the data we have. Now, let me just tell you a couple quick things, and I'm going to stop and take a couple of questions. The RATE project was an 8-year-long project, cost about $1.25 million. It was so successful, not only in fundraising, but the results of the research, that we were encouraged to start several projects like this starting this year after the RATE project was over. The next project we're going to do of that magnitude is the gene project, and we're working with genetics, trying to understand how mutations work and accumulate in our body. One of the first results that came out of this was the mutations occur on the order of about 100 mutations per person, in other words, per generation, and they occur so rapidly that in less than something like 10,000 years, we'd all be dead. If we've been here more than 10,000 years, we wouldn't be here. So that the mutations are really an important issue. It's not in terms of forming new species or new life forms, but making the species, it prevents its viability. It can't continue because after enough information is destroyed in the DNA, it can't function. That's why we're getting more ill with time, our whole population. Anyway, we're going to do a lot more of those kind of studies. The FAST project, by the way, that's Dr. Criswell and Dr. John Sanford are going to be doing that project. These are estimates for some of the costs for it. The FAST project by Dr. Austin is flood-activated sedimentation and tectonics, a major geology project to look at events and processes in the Genesis flood. The Epiphany project is a computer simulation project. We acquired just last month a brand new $75,000 computer that is better than anything Dr. Baumgartner had at Los Alamos National Labs. We have it located and operating at ICR now. It will be doing numerical simulations on the flood, upon climate change, upon genetics, on all kinds of projects. There's something like 8 or 10 different projects we already have planned for being able to do numerical simulations on. I'm quite excited. For one thing, that's what's going to allow me to move up here to the Northwest and do research from Camino Island. I can do it over the internet to the computer back in San Diego. The rate 2, we have a lot of residual questions we didn't answer. So there's going to be more work on that. Studies in cosmology by Dr. Humphreys, and then a whole bunch of miscellaneous projects. And we're also going to be doing a lot of video documentaries. One of the things the RATE project did was to produce a video documentary of the results and the processes in the project. We want to do the same thing on a number of other projects, and we build those into the actual costs of the project in order to be able to report those results technically. Here again is the book that's going to be coming out, the radioisotope book, Radioisotopes in the Age of the Earth. We have a lay version that is actually entitled Thousands, Not Billions. The technical book is going to be about 840 pages. It's written to scientists. This book is about 200 pages written to the lay people by Dr. Don DeYoung. If you ever read any of his books, you know he writes very, very well for the lay public. And then in November, the video documentary is a 48-minute video documentary interviewing all the scientists who were involved in the project, reporting on their results with all these animations that I tried to show you here and did to more or less degree. And then finally, I need to tell you there's a brochure on the back table advertising a RATE conference this November 5th in San Diego, in which we're giving the premiere of the video documentary. The books will all be available at that time. They're just about ready to go to the printer right now, and at that conference we'll have all the scientists there to be able to present their evidence themselves and talk with you directly. So if you're interested in that, that occurs on November the 5th. Thank you. Chris?